You know when you stream a movie or shoot off an email and all that data just zips across the globe in a heartbeat? It feels like magic. While the unsung hero behind all of that is the router. Think of it as the traffic cop of the digital world. So today, let's dive into the router's mind and see how it really works. For every single piece of data you send, every tiny packet, a router somewhere is making a decision in just milliseconds. It's this constant, high-speed flood of choices that decides if your data gets where it's going or just gets lost. So how on earth does it do it? Okay, so if you look under the hood, a router's super complex job really boils down to two main things. It's all about thinking and then acting. First, the router's got to figure out the absolute best path for a packet to take. Then, once it's made up its mind, it has to physically push that packet along the path. Now, these two things are linked for sure, but they are totally separate processes. So first, let's look at how the router thinks. You know, how it chooses that best path.
The router's brain is basically a database, and we call it the routing table. And this entire table, its whole decision-making process, runs on one single fundamental principle. It's called the longest match rule.
The core idea here is actually surprisingly simple. If a packet's destination could fit into a bunch of different routes, the router just asks one question: which route is the most specific? That prefix length just tells the router how many bits of the address have to match. So a longer prefix means a more specific match. It's kind of like a mailing address, right? Choosing the full street address is always going to be better than just the city name. More specific is always better. Let's see this in action. Okay, so our packet is headed for 172.16.0.10. The router checks its table and finds three possible routes. The packet's address matches the first 12 bits of the first route, the first 18 of the second one, and the first 26 of the third one. Technically, they're all valid matches, but because 26 is the longest prefix, the /26 route wins every single time. It is simply the most specific direction the router has. Okay, so that's how the router uses its table. But that brings up the next obvious question, right? How does all this information, this whole map of the internet, get into the routing table in the first place? It's definitely not magic. Routers learn about networks in a few key ways. The most basic way is through direct connections, networks that are physically plugged right into it. Then you have static routes, where a human administrator literally tells the router, hey, here's a specific path. But the most powerful method is through dynamic protocols, where routers talk to each other and learn the map together. And finally, you have the all-important safety net, the default route. So what's so clever about this default route? Well, think about it. A router can't possibly know a route to every single website on the entire internet. The default route, with its prefix length of 0, technically matches everything. But because its match length is the shortest one possible, it only ever gets used if the router has no other more specific instructions. It's the ultimate fallback plan. If you have no idea, just send it this way. All right, this leads us to a new puzzle. What happens when a router learns about the exact same destination from two different sources? Like, what if a network administrator manually sets up a static route, but the router also learns a different path to that same place from a neighbor router using a dynamic protocol like OSPF? Who does it believe?
This is where something called administrative distance, or AD, comes into play. Just think of it like a trustworthiness score for every source of information. And the rule is simple. The lower the score, the more believable the source. A router uses AD as the ultimate tiebreaker to decide which info it's going to put in its routing table and actually use.
And this creates a really clear hierarchy of trust. A directly connected network has an AD of 0, you can't beat it. A static route put in by an admin gets an AD of 1, highly, highly trusted. But a route learned from the OSPF protocol, that has an AD of 110. So if a router has a static route and an OSPF route to the very same destination, the static route wins, hands down, because 1 is lower than 110. The OSPF route is basically ignored unless that static one disappears. So there we have it. The router has used the longest match rule and administrative distance to pick the one single best path. Its thinking part is done. Now we get to the second part of its mission, the physical action of actually forwarding that packet. A packet's journey through a router is this really cool process of unwrapping and rewrapping. A frame arrives, and the router strips it open to see the IP packet inside. It does its route lookup, and then, and this part is absolutely critical, it wraps that IP packet in a brand new frame that's perfect for the next leg of the journey. That original envelope, it's completely destroyed and rebuilt at every single router hop.
Of course, doing all this for millions of packets a second takes incredible speed. Early routers used something called process switching, where the main CPU had to handle every single packet, and that created a huge bottleneck. Then came fast switching, which cached the path of the first packet. But the modern standard is Cisco Express Forwarding, or CF. It pre-calculates all the forwarding paths, so when a packet arrives, the decision is already made, and it can be handled in dedicated hardware, completely bypassing the main CPU. It's literally what makes the modern internet possible. So let's zoom back out for a second. When you put all these pieces together, the decision logic, the ways it learns, the forwarding action, you start to see how this incredible system works on a global scale. And it's really important to get that static and dynamic routing aren't enemies. They're just different tools for different jobs. Static routing gives you precise control and uses almost no resources, perfect for small, predictable networks. Dynamic routing gives you automation and adaptability, which is essential for huge, complex networks that have to react to changes on the fly. In reality, most networks use a mix of both. And this brings us to a really mind-bending fact about how the internet actually works. It's not one giant unified network with a single map of everything. It's a massive distributed system where every single router makes its own independent decisions based only on its own local information. It's a chain of these independent choices, each one just trying to get a packet one step closer to where it needs to go. And that's really the final thought to leave you with. This intricate dance of algorithms, trust scores, and local decisions happening billions of times every second in routers all over the globe. This is the invisible system that powers our entire digital world. It's a high-speed logic puzzle that somehow, almost miraculously, just works.